Dear students, in this video we will recall the finite differences and interpolation, which we have already started in the previous class. So we have already discussed about the finite differences. The calculus of finite differences deals with the change in the values of the function f of x due to the change in the independent variable. And we have already discussed that we are having two types of data. In first type of data points, where this difference between x0 and x1 and x2, this is fixed. For example, here the distance is h, and corresponding data will be f of x0 plus h, and so on. In the second type of data, generally we are having variable distances between x0 and x1, x2 and x2, and so on. So we are having two types of data points, and based on this category we are having two types of methods, two category of methods. Now if what is our problem is, with the help of this given data, our aim is to find out the value of the function at some point within the range, this is, or the derivative of the function within this range, or integration of the function within this range. So this is the problem of interpolation. If we are finding f of x, f dash x outside the range, then this process is called as extrapolation. This we have already discussed in the class. These are the assumptions of interpolation. That means we are dealing only the problem in which the problem is that we want to find out fx, f dash x within the range. So what are the assumptions? We have already discussed about those assumptions, that there are no sudden jumps and falls in the values during the period under consideration. The rise and falls in the values should be uniform, and the given set of data can be expressible as a polynomial. So here we are discussing the polynomial interpolation. We are not considering trigonometric, exponential, etc. So what is polynomial interpolation and interpolating polynomial? If the function f of x is not known, then to find f at some point within this range x0 to xn, because the data is within this range from x0 to xn. So here x is in between there, then it is required to find simpler function, say phi of x, such that f of x and phi of x agree at the set of given points. Here f of x is actually the true function, and phi of x is the approximated function. This is known as the interpolating polynomial, and graphically you can understood this as this. Here we have, suppose this is the data pattern. This is the data pattern, and the exact curve is, for example, this is the exact curve if f of x is known to you. This is f of x, but since we don't know exact f of x, we know only the points. Here this is x0, this is say x1, x2, this is say x3, this is say x4, this is say x5, and so on. So since we don't know the exact function f of x, we know only these points. We have information about these points only. So our target is to find out f of x, f dash x, etc. at the point x within this range. For example, say last point is this. Suppose this is xn. So within this range from x0, suppose this is x0. Here this is x0 to xn. The target is this. So since we don't know about this intermediate parts, we don't know about the information, because f of x is unknown to us. So in that case, our target is to fit a polynomial which satisfy these interpolating conditions. This, for example, say this type of pattern we have. So this red curve is actually our phi of x. This is called as interpolating polynomial. This is our interpolating polynomial. This is the true curve or true function. This is the interpolating condition. And interpolating means, because you can see that f of x and phi of x, they are coinciding at the given points. That means f of x is phi of x at x is equals to xi. Here I varies from 0, 1, 2 to n. And this is known as interpolating condition. We have already discussed this thing in our previous class. So now our target is to find out this phi of x. Phi of x. So for this we have methods. Three commonly known methods are graphical method, method of curve fitting, finite difference method. So since our focus is here in this finite difference, with the help of differences we will try to find out phi of x interpolating. So now first we will discuss about the merits and demerits of this. So merits of finite difference: it does not assume the form of the function to be known. There is no need to find out the exact form of the function. Just only requirement is that we need only the data points. Less approximate than other methods, simple to apply and takes less calculation. So this is a simple method. What are the demerits? There is no defined way to verify whether the assumption for the application of finite difference calculus are valid for the given set of observations. So these are the merits and demerits. Now, since our focus is on finite differences, so here we will discuss about the finite differences. And here we will take fixed step size. That means first data type points when the differences are constant. Fine. So to start this finite differences, first understood the types of the differences. Here we have three types of differences: forward difference, backward difference, and central difference. These are the three important types of differences. Forward difference is denoted by this delta, backward difference is denoted by this nebula, and central difference is denoted by this Kronecker delta. Kronecker delta. Fine. So now we will study forward difference, backward difference, and central difference in the next video. Thank you.